provide more than just the final. I want to go through some of the processes that have produced these mountains, and I want to take a vote on how we do the lights.
That's good.
Like that?
Yeah.
Yeah. Okay. If I have to show a rock, I'll just hold it out over here. Okay. What I want to do, show some, really give you some understanding of the hows and whys. I also want to spend some time talking about some specific sites down in Panthertown and my thoughts about how they came to be the way they are. All that's going to take me a bit over an hour, and then I'll be delighted to have a question and answer session. And if people get tired of that, I'll be happy to hang around for individual questions as well. Now, to tell a story, you really have to have a starting point. And when you're talking about something like what the Earth looks like, that's not entirely obvious. You can make a plausible argument for going back to the Big Bang, I suppose. Certainly back to the formation of the Earth, that'd be 4.5 billion years. All that's a bit much to bite on. So I've chosen a much more recent starting date. I'm going back for the starting date of 500 million years. Nice round number, but there's a lot more going for that number than just being round. The main reason I chose that number is that 500 million years ago, what I call the parent rocks of the country rock of the eastern Blue Ridge had formed, and something very interesting was beginning to happen. Now I'm going to break that one down for you. What is the eastern Blue Ridge? Well, you think of it as roughly the eastern 1/3 of the Appalachians, all the way from North Georgia up into southern Pennsylvania. And what is the country rock? Well, let me back up. Around here, the eastern Blue Ridge would run from the bottom of the escarpment down near Salem, South Carolina, up and across to the Cullowhee-Tuckasegee area. In short, it's the area in which Panthertown and Cashiers are located. Now, what is the country rock of this geologic area that we are located in? Well, that is the predominant rock. That's the rock in which and on which everything else has happened. It's the rock, if you go out and kick a rock, you're kicking that rock unless something unusual has happened there. And there have been unusual things. We will get to other rocks. And what do I mean by the parent rocks? Well, those are the rocks that aren't the country rock, but they are the rocks that over time and through processes that I will talk about, became the country rocks. Well, I hope you might wonder, where were they formed up? Where were they located 500 million years ago? The answer to that is, they were not up here. In fact, they weren't even on dry land. They were at the bottom of an ocean. It's an ocean that geologists call the Iapetus Ocean. You can think of it as the predecessor of the Atlantic Ocean, although I'm going to continue to call it the Iapetus during this presentation.
Sorry.
I actually remembered to cut mine off earlier. Yeah. Now, the Iapetus Ocean lapped up against a continental landmass that was the predecessor of North America. Of course, geologists gave that a different name, but to keep things simple, I'm going to call it North America. And that landmass, like all large land masses, particularly those that were down in tropical regions, which is where North America was 500 million years ago, has rivers running off of it. And they're running down into the Iapetus Ocean, and they're depositing sediments into that ocean. So I think this graphic will help you understand what's going on here. We have over here on the over on the left the North American continental crust, age today about 1.2 billion years old. These particular rocks, and out into this ocean are flowing a variety of sediments. sand, mud, silt. Other stuff's getting added to it, particularly this volcano, a line of volcanoes off our eastern coast back then. And it's throwing out ash that's filtering down into those sediments, and it's throwing out lava that becomes rocks down with those sediments. Over time, these sediments piled up, maybe 3-4 miles thick or so. The stuff on the bottom is under a lot of pressure. The excess water gets pushed out. The remaining water facilitates chemical reactions that cement them together, and they become rocks. They're sedimentary rocks. They're those same sediments that came flowing down off the ancestral North America. They've just been cemented together. And they had names like sandstone, mudstone, siltstone, graywacky. Where'd that one come from? That's muddy sandstone, in case you're wondering. And mixed in with those rocks was some of the basalt as a result of those lava flows that came out of that volcano. All right, so we have our parent rocks, but they're not the rocks we have today, and they're in the wrong place. So what good are they doing us? How do we get from there to our current landscape? Well, the first step is that very interesting thing that was beginning to happen to these rocks 500 million years ago. And here we need to talk for a minute about plate tectonics. I'm sure you've heard the concept. It's the whole phenomenon of the rigid upper layer of the Earth being divided into a dozen or so major and other minor plates. And those plates are resting on top of a layer below them that's not exactly liquid, but it is viscous. It will flow very slowly, measured in inches per year. And as it flows, it moves these plates that are up there on top of it back and forth. Sometimes they go away from each other, other times they approach each other. Well, 500 million years ago, the plate that contains what is today Africa, and that I will call Africa for the purposes of this presentation, was on a collision course with North America. The advanced landing party was that line of volcanic islands that were offshore. Now, we need to look a little bit here at this black tongue that's sticking out in front of North America. It was part of the North American plate. That's basalt, it's ocean crust. All ocean crust all over the world is basalt. It comes out of the mid-ocean ridges. It happens to be about 10% denser than the rocks that you and I walk around on. Now, granite's heavy, but basalt is heavier. So, as the landmass, like this island, starts colliding with that crust, that ocean crust, gravity steps in and says, ocean crust, take a dive. You're heavier, you're going down. And it does. But that volcano, that landmass that's coming on, isn't floating on water. It is grinding across that crust. And what is it doing as it's grinding? It's acting like a great big bulldozer blade that's pushing up the parent rocks and other sediments that hadn't become rocks off that seafloor and pushing them towards our continental crust. Fast forward that about 50 million years, and it looks like this. That island has landed. The continental crust is now buried deeply down here. Our parent rocks are in this sort of region. A lot of stuff piled up on top, including those volcanic islands. This built up a very substantial range of mountains, probably thought to be on the order of the Rockies or maybe the Alps. But the main thing it did in our story is deeply bury our parent rocks. We're talking 8 to 10 miles. At those depths, the heat and the pressure are so great that the rocks change. They go through what is called metamorphosis, and they actually become different rocks. The minerals will rearrange themselves and physically move around. Atoms will leave one mineral and move and form a different mineral somewhere else. And that is how our parent rocks became our country rocks. And they have names, those metamorphosed rocks have names like gneiss, schist, metagraywacke, of course, and the basalt turns into something called amphibolite. Okay, let's back up and I'm going to invite my wife to come on down to this chair that we've saved for Susan. She didn't know I was going to get started so early. I got the schedule going here. Let's back up and think about a moment just about what has just happened. We have had a mixed array of sediments deposited in an ocean. They've been mixed up by ocean waves and underwater landslides. They have settled out, formed into layers, become rocks, and then they have been bulldozed up, pushed up onto the land, where they eventually became buried and pressure cooked. Now, what do you get out of that? Well, what you get is a real mishmash of a rock formation. It's highly varied. Around here we call it the Ashe Metamorphic Suite. You go down into North Georgia, it's called the Tallulah Falls. You go farther north, it's called other things. Geologists all up and down the eastern seaboard, as they started studying this stuff, gave it a local name, and only later learned it was all basically the same phenomenon. Now, this picture is just intended to emphasize how varied this thing can be. We'll see some of this brown stuff up here later at Schoolhouse Falls. This black stuff is the amphibolite, metamorphosed basalt. You've got some other rocks here, gneisses, that you see a lot on, like the top of Whiteside Mountain. But this picture emphasizes how this stuff was just all mixed up together in all kind of very, a lot of variety. And even within some of these particular types of rocks, you get a lot of variety. Now just consider for a moment how different it is from this. This is out in southern Utah, and you have these nice orderly layers. These were laid down in shallow seas, not a lot of activity in them. As sea levels rose and fell, you'd get different layers. And at one time when the sea levels were particularly low, you got this white windblown formation there. But this is all very orderly, and it makes a totally different type of landscape than we have here. Now, one of my favorite rocks in the Ashe Metamorphic Suite is this guy. It's a Mica schist. After I got familiar with what it was, I realized that I've got these all over my yard. I've been collecting them for dozens, for a long time because I liked them as stepping stones. This runs along, you can find this. This stuff runs in narrow bands, a few hundred yards typically. And one of those bands runs across the top of the trail, the ridge that goes up from Salt Rock to Blackrock Mountain. Now, other places that you'll find Ashe Metamorphic Suite, which, by the way, is a perfect name for this stuff. It is a suite of rocks, as you can see. What they all have in common is that they are the metamorphosed versions of rocks that formed up under an ocean. Ashe is for Ashe County, where it was first studied in North Carolina. But the tops of Whiteside, Sheep Cliff, and Chimney Top Mountains are all Ashe Metamorphic. Yellow Mountain is totally Ashe Metamorphic, as is Toxaway Mountain once you get out towards the tower. everything around Asheville. The Blue Ridge Parkway from up in Virginia on down to Richland Balsam, which is the high point of the parkway, kind of up above the Cullowhee-Tuckasegee area. And Mount Mitchell and the great craggy mountains, those big mountain ranges north of Asheville. It's all Ashe metamorphic. But you and I know we aren't Asheville. We got something more, and it's part of what makes us special. And that's the plutons. Now, big green is an exposure of a pluton. A pluton is magma, that's melted rock, that has formed up in the earth but has not made it to the surface. If it makes it to the surface, it's called lava. This stuff solidifies underground, and because it solidifies underground, it solidifies slowly. When a rock solidifies slowly, the molecules of the various minerals have a chance to find each other, come together, form crystals that are large enough to be seen with your naked eye. And that's pretty much the definition of granite, when those crystals are consist of feldspar and quartz with scattered mica. Now around here, the big pluton is called the Whiteside Pluton. It, of course, is named for this guy. A little bit ironically, however, only about half of it is actually Whiteside Pluton. The upper half, as I mentioned earlier, is Ashe Metamorphic, and you can see the dividing line kind of goes across here. It's also the case that the Whiteside Pluton is a whole lot more than Whiteside Mountain. It is all around Cashiers, the big road cut on Highway 64. That is the same rock as the bottom half of Whiteside Mountain. It's Whiteside Pluton. And it's all around Panthertown. Big Green, Little Green, Coal Mountain, Shelton Pisgah, the flanks of Blackrock Mountain, Salt Rock up here in the foreground. And for that matter, take the trail from Salt Rock down through the valley around Little Green to Schoolhouse. And until you get to Schoolhouse, virtually every rock that you will see, every rock you see is going to be Whiteside Pluton unless somebody hauled it in there. And there have been a few of those. Other places you will find the Whiteside Pluton out in Lonesome Valley, Laurel Knob and Cow Rock. Bald Rock is all Whiteside Pluton. Rock Mountain down here is Whiteside Pluton, and most of Chimney Top, but not the very top of Chimney Top Mountain. It's really quite extensive, and this map, I think, will help you appreciate how extensive. Now, I know you can't read that from here, and I'll ask you now just to pay attention to the orange. The other colors we'll get to later. This black line around the outside, that's my definition of the Highlands Cashiers Plateau, or at least what us lay people would call the Highlands Cashiers Plateau. It's not really recognized in the geological literature, but it's a little bit of a different subject maybe. To get you oriented, Highlands is down here, Cashiers is here, Lake Glenville is up here, Panthertown is in here, and then the orange goes on up towards Balsam Grove, doesn't quite get there, that's the town up Highway 215. These white splotches down here in the orange, this is the top of Whiteside Mountain. This is the top of Sheep Cliff. Over time, I expect this orange portion of this map to grow. More of the Ashe Metamorphic is going to be eroded away. And I expect it to show more Pluton coming to the surface. These are the rocks that are at the surface currently. North to south is sort of from Chimney Top up to the northern edge of Lake Glenville. You will find outcrops of the Whiteside Pluton. So it's our home rock. Let's talk about it some more. First, it's quite veined. Got a lot of these sort of this veins that are particularly rich in the white minerals, which are feldspar and quartz. It's quite varied. All of these rocks, and I've got others up here later if you come up and look, they don't look much like each other, but they're all Whiteside Pluton. And I'll discuss later why this might be a characteristic of that Pluton. The age has been determined at 466 million years ago. Now, the scientific literature will say 466 plus or minus 10. And all of these ages that I'll be giving you are subject to a margin of error that is typically 1 to 2%. So the ages are not quite as precise as this may make them appear. Now, how is that determined? It's radiometric testing. That's the same techniques that are used to use carbon-14 to determine the age of a mummy, for example. However, in the case of rocks, it uses different elements and different isotopes that are found in the rocks and that have atomic characteristics that make them work for these very long ages. Another thing about the Whiteside Pluton is it's white, or at least it's certainly very light. The reason for that is that it's quite rich in quartz and feldspar, both of which are very light minerals. It's because of this that we have so much white sand in our ditches around here. That's where the Whiteside Pluton has degraded, and most of what's left is in the ditches, and what have you is quartz. Now, one of the things that I really love about the geology of this area is that it does have this mixture of the Pluton and the old country rock. And that creates some interesting stuff. And just think of the setting here. You're the country rock, Ashe Metamorphic. You're laying there doing what a rock's supposed to do. You're probably pretty irritated because you're under a lot of heat and pressure. And then up comes this molten mass of rock, pushing up into you, around you, through you. Interesting things you would expect to happen, and they do. One of them is called pegmatite, stands for mixed rock. That's the white stuff that somehow has gotten into this layer of black rock. How did that happen? Well, when this Pluton comes up, this molten rock, it's got a lot of heat. There may not be enough heat to actually melt the rocks above it, but it will partially melt them sometimes. And what minerals are going to first melt when a rock is partially melting? Well, it's the minerals with the lower melting temperatures. And that happens to be quartz and feldspar in these rocks. So these light minerals melt, they become free to kind of move around among the other molecules of the rock. They seek each other out, find each other, come together, and ooze around in these very interesting sort of patterns that you see here. Another thing that happens is all that heat and pressure increases the metamorphic conditions. It makes for a higher level of metamorphosis. And one of the things you'll get is something like this. These are pods of garnet. It's an unusually dense collection of unusually large pods. Garnet only forms under very high metamorphic conditions and is explained in this sort of setting by the additional heat and pressure that was added by the Pluton. Now, don't get excited. These aren't gem quality. They might have been mined at one point for industrial purposes, but they weren't. And the reason is they're not very accessible. They're kind of up in here. And to check them out, you need some friends with climbing expertise and equipment. But you don't have to go climbing to see pegmatite. Just drive up Cedar Creek Road You're familiar with that last long sort of straightaway before you get to the hairpin at the very top. Well, at the bottom of that straightaway, it's Whiteside Pluton. At the top, it's Ashe Metamorphic. They meet along the way, and you will find up higher in the Ashe Metamorphic some very nice exposures of pegmatite. This one is above that small waterfall and just before you get a little bit below the hairpin. Another thing that forms in these contact zones is something called pegmatite. Now, that's this guy shown large there. What a pegmatite is you got a chamber in the rock where you have the rock completely melted. It's often up in the country rock, and you have conditions, for whatever reasons, of moisture, the minerals, and chemistry that keeps that rock fluid for an extremely long time. And when that rock stays fluid for a long time, it's able to form some very large crystals of the type that you see here in this rock, which is a mixture of feldspar, large feldspar crystals, and a lot of quartz and mica. But that's where I got these guys. You don't find this stuff just kind of walking around in normal old Ashe Metamorphic. Something interesting has to have happened to have created those. These pegmatites, and these chambers, by the way, I mean, they can range from a few feet to the size of a house. And the larger ones are where mica mining and occasional feldspar mining occurred up here on the plateau. Mainly off and on back in the first half of the 20th century. Why is that? Why was it there? Because that's where the mica could grow large enough to be commercially interesting. Now, I really can't tell you where to go find a pegmatite mine. They are poorly mapped. They're almost all on private property. They're overgrown. But you can see a pegmatite by walking down to Schoolhouse Falls. That's a small vein. If you're looking at the falls, the path around under it on the right, you'll find this little vein of pegmatite. So while we're at Schoolhouse Falls, let's talk a little bit about how the intersection of the country rock, Ashe Metamorphic, and the Pluton has shaped that falls. If you go around to the left, you're probably to go under the falls, you'll have encountered this overhang that's slanting down into the ground, sort of forms a cave back up in there. All of this is Ashe Metamorphic. Now, notice it's got a lot of fractures in it. Those fractures, it's hard to tell from the picture, but they're all pointed up kind of out over the pool. And as water comes down, seeps down across this surface, those fractures are going to catch it. Water gets in there, the rock weakens, maybe it freezes and thaws, and stuff continues to pop off the bottom. This overhang and the ledge of the falls will continue to move upstream as that process continues. And it's that process creating this sharp ledge at the top that creates the vertical drop that you have in the waterfall. But now look where that fall lands. That's the landing zone for the water. Totally different rock. It doesn't have all those fractures. It's really solid, and it even slopes in a different direction. That's Pluton. Now, compare the character of Schoolhouse Falls with a fall that is all Pluton, like Warden's Falls. Yeah, it's complex, but it doesn't have the type of vertical ledge. And it's more rolling, and you have smoother surfaces that the water is coming across. And we're not the only, and I'll get back to that subject later. I'll explain why that's the case. Before I get there, I want to talk a little bit about the other plutons that we have up here on what I like to call the plateau. We actually have the highest concentration in the eastern Blue Ridge, part of what makes us so special up here. There are several smaller ones that are up on the northern periphery. I'm not going to talk about those right now. And I do want to point out, too, this long blue guy is the Raven Pluton. It runs right across the spillway of Lake Linville, goes on down towards Tuckasegee a little bit, then in the other direction goes down into North Georgia, into Raven County, which is where it gets its name. The pink guy over here is the Toxaway Gneiss. Lake Toxaway is up in here. This is what's exposed at the falls up there. Comes down across Whitewater Falls, and then on down in South Carolina, it crosses Wigington Road. There's a nice exposure of it across the road and down a little bit from the big overlook on Wigington Road. Let's talk about these just a little bit. The Raven, that's the one out Lake Linville, notice its age. 335 million years, a lot younger than the Whiteside Pluton. We'll come back to that later, explain why that happened. What fascinates me, I really like about this one, you look down in the spillway from the bridge, this is Pluton, and over here is Ashe Metamorphic. They meet right there. You then turn around and look at the dam. You know, it's really quite visually nice. I don't know whether the designers intended it that way, but they faced that dam with the rock they had at hand, and that rock was a mixture of the Ashe Metamorphic and the Raven Pluton. A couple others, mainly notice the dates, all right around the same time as the Raven. Again, a lot younger than the Whiteside, which is 466. The Walnut Creek runs across Cullowhee Mountain. The Looking Glass comes over and intrudes into my map area just a little bit, but of course it's much better known for its namesake exposure, Looking Glass Rock, over is seen here from the Parkway. Round Mountain is a very small one. It's way off on the north. It's up on 281, which is north of Lake Toxaway, as you start going down into Little Canada. But the reason I wanted to show it is this is the most precise contact between a Pluton and our country rock that I have found or seen. The Pluton is the gray stuff here. The brown stuff with some pegmatite, whoa, hit something, with the pegmatite mixed in is the Ashe Metamorphic. Literally, stand there, put your right hand on this seam. The rock under your little finger is 200 million years younger than the rock under your thumb. Toxaway Gneiss, I mentioned earlier, that is well exposed at the spillway from Lake Toxaway, but you don't have to go out there to see it. If you drive around the roads here and happen to look at any ditch that has riprap in it, you're looking at Toxaway Gneiss. And that's also true of almost any other construction grade stone that you see up here. The reason for that is the McNeely Quarry, where all our rock comes from, down on 281 south of Sapphire, located right in the middle of the Toxaway Gneiss. Now, if you look at some of those rocks in those ditches, you'll see it's really a very distinctive rock. It's heavily banded at various scales. You have this band of predominantly feldspar and quartz. You also have these very narrow little lines of mica. It used to be like that stuff on the right. Stuff on the right is the Raven granite. What has happened is this has been metamorphosed. I'm not telling you how old this is yet, but is a lot older than the stuff over here, the Raven granite. It actually has been through 2 episodes of metamorphosis. But you can see here, I think, very clearly how metamorphosis literally and physically rearranges the minerals and the grains in this rock. Stuff gathers together into these bands. All this very fine-grained stuff down here, that's little rows of mica. And mica, of course, is a flat plating mineral, and it has, those grains, in addition to kind of coming together, have been pushed flat by the intense metamorphic pressure, the intense physical pressure that in this picture would have been up and down. And they've been pressed flat against that, that pressure, and it creates these very fine lines. All right, with that little introduction, what is that? Gneiss or granite? That kind of depends on which piece of rock you look at, I guess, if you're looking for what you just saw. Don't feel bad. Geologists have called it both over the last century. The name I like the most actually is Cashiers gneiss, but for the Whiteside, but that never caught on. In the last 15 years or so, there's been some pretty serious mapping done up here by both the a graduate school research programs and also a U.S. Geological Society up around Highlands and Whiteside Mountain. And all of those maps say this is granite. They will say that some of these specimens are gneissic granite. Whoa. Anybody? Yeah, I have no idea what just happened. Here, this is.
Plugged in?
I am totally plugged in. Make sure I didn't. Oh, wait a minute. Wait a minute. This can be
Totally
plugged
plugged into
in.
the computer, just not to the outlet.
That's why I knocked that out. Okay, it may take it a moment to come back up. Hopefully that'll get her going. No, it still had plenty of power. I don't know how that would have affected it. Yeah. And anything else unplugged? And this is the cable that goes over there, and it seems to be secure. Well, he's seeing if he can find something. I'll continue to talk about this a little bit. Those maps all say it's granite. And I think what's going on here is that gneiss is a metamorphic rock. To be a metamorphic rock, you have to have formed up as one rock and then been changed by pressures in the earth to a different rock. So I believe that implicit in their categorizing this as granite is the conclusion that this rock formed up pretty much like it appears today. That it has not been undergone metamorphosis. Now, yeah, maybe if you reboot that, it'll get it going. But remember when this formed up. That was 466 million years ago. And of course what was that's right in the middle of the period that our Ashe metamorphic was getting pushed up, been deeply buried, and it was being pressure cooked. So it came up into an environment that was with very heavy metamorphic pressures going on. Now, those metamorphic pressures never had the opportunity to, I'll say it, commit metamorphosis on the Whiteside Pluton. So, but it did affect the Whiteside Pluton. And it's believed that those effects are reflected. Lost the mic now. Are reflected in the variability and the gneissic characteristics of that rock as it formed up. And that's believed to explain that variability that I talked about earlier. All right, we need to get back to our main storyline. Maybe with or without my pictures. Where we left off 450 million years ago, our rocks, our country rock had formed, our main Pluton was in place, but it's nowhere close to today's environment or today's landscape. There are a couple of big problems. One is that we're buried 8 to 10 miles. Another is we're about 150, 200 miles to the east. Hadn't mentioned that one, had I? Something had to happen to deal with that. Well, you guessed it, plate tectonics. Africa kept coming for about another 150 million years. This time it was a little different collision because that tongue of ocean basalt that the island rode up over was no longer there. It was two land masses banging into each other. Both of them were a similar density. Gravity is not telling one to go take a dive. They're going to duke it out on the surface. Still a tremendous amount of material that's got to be moved out of the way, and if none's going to go down, there are only two choices. Get pushed off to the side or go up. Well, going up is what's happening in the Himalayas today. It's still rising at about 2 inches a year, and that's propelled by the collision of two land masses, the Indian plate and the Asian plate. We had the same thing here at this point, back between 300 and 350 million years ago. But those mountains are not really our ancestors. There was a huge range of mountains built up, probably on the order between the Andes and the Himalayas today. But they were located, centered out on the Piedmont. We were on the periphery of those mountains. But the other alternative, getting broken off and pushed to the side, has directly affected our landscape. The Eastern Blue Ridge was part of a huge slab that was broken off and slid across North America by something like 200 miles. The western edge of that large landmass, of that large slab around this area, you now call the Great Smoky Mountains. If you go out there, you can see places where it has eroded through, and you're actually standing on the rock that it got slid out over, and it's the same rock that is spread across the rest of Tennessee. Cades Cove is the classic example of that one. Now, the other thing that happened with this collision, these collisions are very conducive to forming underground magma chambers. Remember, the Whiteside Pluton formed up 466 million years ago when there was a collision with that island chain going on. These younger Plutons, the Raven and other 335 million sort of stuff, formed up during this event. And the magma chambers eventually became these Plutons. Now, we're getting closer. We're in the right place, but there are some problems. We're still buried, not nearly as deep as we used to be because there's been a lot of erosion. But there's this huge mountain range that's located off to our east, And there's also no ocean in sight. So what took care of that? The reason there was no ocean in sight is at that point, after Africa collided with North America, we were in the middle of a huge landmass called Pangaea. Pangaea is the last time that a supercontinent formed up, as all of the Earth's land masses basically came together as a result of plate tectonics into one large mass. So a lot of stuff had to move away from us in order to get to our present landscape. So what happened? Well, Pangaea began to erode, both to the east and the west. And you know whether you remember that wind-blown white formation in the picture of southern Utah. That's actually believed to be from sediments that came from the Appalachians, transported out there by a combination of wind, of river first, and then wind deposited over a vast area of the American Southwest, where it eventually became the Navajo sandstone, much to the delight, I might add, of mountain bikers out around Moab, Utah. But more importantly around here, Pangaea was fairly short-lived. It began rifting apart about 200 million years ago. And as it did, some of the eroded remains of those mountains to the east went with Africa. They're now, you can find them in Morocco. Other of those big mountains subsided as the Earth, as it rifted apart, as it pulled apart. The crust stretched, it thinned, and those big mountains would not have had as much support, and they would have sunk down some. The Atlantic Ocean formed, and then you just had many millions of years of more erosion. They finished off those big mountains. They're now deposited largely as part of the coastal plain in the continental shelf. And as all that happened, our current landscape began to come to the surface. Now, I would really like to have some of my pictures for some of the more of this discussion. And I'm going to reboot my computer. Yeah, I'm on take a minute, and maybe if you'd like to take a quick break while I get this thing to reboot, we'll see if we have a better chance.
You have it on your screen, it's just not being projected?
Yeah, it's on my screen, but it's not being projected. That's it may be, yeah, I'm afraid it might be the cable. It's not my cable, it's the library's cable.
There we go. There we go. And there's your computer screen.
Okay.
That's progress.
Yeah, I didn't even reboot it. I just put it to sleep and woke it up.
That's awesome.
I was aggravated with myself for hitting the go to sleep.
You're projected.
Yeah.
It took about 10 minutes to reboot it. I'm really sorry.
Oh, is it up there?
It's up there. Yeah, it had nothing to do with you.
Okay.
It's the projection system for the
I don't know what happened. I rebooted the thing, Bill, and it's come back up, but it has to warm up.
All right, well, you're back.
Yeah. No, I'm fine. Yeah,
Technology.
Yeah. Let's let people have 5 minutes. And, okay, we're going. We'll take about 5 minutes to, if you want to get something to eat, you can get some water or whatever. And I'll roll forward.
These are all the stars of the show?
Yeah, there you go.
The pattern as well. Sit up so close. I'll use this time to get
It'll make a lot more sense with the visuals. While we're waiting, if you'd like, we do have some raffle tickets over here, and we have maps, t-shirts, and we can certainly answer any questions you might have in the next 5 minutes about Panthertown. If you did not already get one, we have door prize tickets. We're going to give away some door prizes.
I told you, I'm a
You
one.
can go see Maggie at the back there, and she'll get you one.
Yeah, I was getting fascinated. As I said earlier, all sort of resources. Introductory text, doctoral situations, online courses, field trips.
There's a question about I heard that terminology, the Whiteside Pluton. If you were to excavate Whiteside, is the Pluton continue to go down?
Well, people have drilled dry holes on that stuff for water thousands. It goes down the
Pluton, and it's
I don't think anybody, it's believed that it's been talked about.
It's magma.
It was magma. Yeah, it was a proven. No, it isn't. It just sort of.
So when you go like there, you stare at it.
Well, it's only called lava if it's molten when it comes to the surface.
But I mean, it was at one point.
It's all magma.
Yeah, there had to be somebody in here that figured that out, right?
Just needed to, they had to reboot it back
They
then.
had to reboot it.
Yeah, it wasn't that.
That's what it looked like. Had to reboot, but it didn't look like this had to be rebooted.
I know, I didn't think it was it, but I was going to try it.
It was still just as good.
I'd like to thank Auburn Friedman from the Canary Coalition for being here and helping to live stream this presentation tonight for those who could not be here this evening. This is being recorded. It will be available to play back from our website. And also right now, folks that are watching through the web feed are here as well. So we have about 120 people in the room here tonight, which is great. It's fabulous. Thank you all for showing up and being here. And we have brought some more chairs in, so for those who have arrived late, if you have not had a chance to sit down, we can get you a place to sit. And Bill Jacobs will be coming back in about a minute.
Back by the crowd.
Let's give away some goodies. Right here I have 3 door prizes in my hand, so get your door prize ticket out. We're gonna draw for 3 door prizes and then we'll throw it back to Bill. Our first door prize is a DVD of Friends of Panthertown. Tells you a little bit about what we do and has a nice slideshow of all the flowers and plants that are in the valley. And that first ticket will be 615400. It's number 400 here. All right, we'll come back to that one. 615340. Okay. 615313. We have a winner. All right, I'm going to actually throw it back to Bill right now. We'll do the rest of our door prizes after the presentation.
Okay. Thank you all for your being understanding. Apparently the library system had a hiccup and had to be rebooted. Okay, where we were is that I had said that as this erosion process proceeded, our current mountains, our current landscape slowly appeared at the surface. But what I really want to emphasize is that what you see today is not a mirror twin of anything that used to be. It is not the case that what used to be higher is now higher and what used to be lower is now lower. Our current landscape is the product of erosion patterns and erosion activity in fairly recent geological times. It's not the effect of how things were 25 million years ago. And erosion is affected by a wide variety of things other than the underlying bedrock and this marvelous epic geological history that we've been talking about. Climate, local weather, vegetation cover, plain old accidents of nature all have an impact. But I know it's not going to be very satisfying to you if after all this I stand up here and say, well, the reason things look here like they do here in Cashiers Valley and Panthertown today is just the way erosion worked out over the last X million years. I'd like to try to do a little better than that. And so what I'm going to do is talk some about how the characteristics of our two rock families would likely have contributed to the landscape that we see today. Our plutons and our country rock, the Ashe Metamorphic suite. So I'll be talking about what are the erosion characteristics of those sets of rocks. And the main factors at that level are going to be the resistance of the rocks and their fracture patterns. Now resistance is probably the easy one to understand. I'm talking about how well does the rock hold up to abrasion, to chemical weathering from acid and what have you that it encounters in the environment. A great example of the dramatic difference that a relative resistance, a highly resistant rock, can make is Mount Mitchell. And it's almost as tall brethren up in the Black Mountains north of Asheville. Mount Mitchell is Ashe Metamorphic, but it's composed of metamorphosed sandstone. And now sandstone has a lot of quartz in it, and quartz is tough, and it doesn't chemically react very readily. But the sandstone that Mount Mitchell formed from was also unusually rich in aluminum. Now aluminum is not particularly hard metal, but you combine it with quartz and it makes a very hard and very resistant rock. And therein lies a major explanation, probably others, the world is complex, but a major part of the explanation for why Mount Mitchell is now the highest point in the eastern United States. But I really don't think resistance and the relative resistance of the two sets of rocks has played a big role in our landscape. I know that you expect the Pluton to be pretty tough. It's got a lot of quartz in it. But I'll remind you that the highest places on our plateau are all Ashe Metamorphic. Yellow Mountain, top of Whiteside, top of Chimney Top, top of Toxaway Mountain. So something else is going on. The Ashe Metamorphic that you'll find up at those locations also have a lot of quartz and feldspar, very similar mineralogical content to the Pluton. So I think fracturing and different fracturing characteristics have played a much bigger role in our today's landscape. Now, why would fracturing be important? Well, when a rock fractures, water gets in. Water gets in it, it brings in acid rain. It brings in microbial life. Eventually, you get soils forming. roots. You get freeze thaw. When a rock is fractured, it is much more vulnerable to erosion. So what I'm going to do now is give you 3 generalizations about how fracturing and erosion of our rocks would likely could have contributed to the landscape and the features that we see as we walk around the plateau in Panthertown. But first comes a big disclaimer. Surface of the earth is very complex. The things that I'm outlining are matters of degree and frequency. They're not absolutes. And there are always exceptions. And of course, in science, an exception is not a bad thing. Exception drives you to try to figure out, well, how do I need to refine this generalization? Or is there some other process? It helps drive science forward. But with this disclaimer, generalization number 1, high ridges created by crustal folding can turn into low valleys. All right, what do I mean by that? Well, first, what is crustal folding? Well, that's pretty much what it says. It's where you get the crust of the earth doing that, getting high ridges and valleys. Well, how could that happen? Well, remember how we were part of a huge slab that got pushed about 200 miles from the up to the northwest. We weren't on greased rails. There was a tremendous amount of resistance to that rock layer being pushed across the layers below it. The combination of that resistance and the huge amount of force being applied by Africa as it was landing would have compressed that rock, that slab. And that compression would have expressed itself in folds. Okay, we've got folds. We've got high points, we've got low points. Why would they reverse position? Well, for that, I'm going to use an analogy to take a cake, a layer of cake, press it from the sides, compress it, it'll bow up. But what are you going to have along the top? You're going to have a fracture. Same thing happens at the top of these folds in the crust of the earth. Water gets in, before long you have a river, and eventually it becomes a low valley. Now, we believe that you can see this right in Panthertown. First, you might ask, well, how do people know where there used to be a high ridge that's no longer there, or a fold that no longer is there? Well, the answer to that is that when geologists are mapping, they're not just writing down the type of rock that they're finding. They are also studying the direction and angle of rock layers. And when they find a layer over here that's pointed up like that, and over here they find the same layer pointed up like that, the conclusion is those layers used to meet at the top. Some Western students in their geology department in the last few years did that type of mapping down in Panthertown. And what they found was that they believed that there was one of these ridges from folds going over the top of this center of the valley. And actually they mapped it to sort of bend around the end of Little Green down here and head on down towards where the Tuckasegee River heads off on down towards Little Canada. Now, 50 years ago, a doctoral student did some mapping up here. The only man to have ever actually mapped Cashiers. By today's standards, it's certainly not as detailed a map as current mapping, but it too shows this same structure. And on his map, the ridge of that fold goes on off to the south, to the west, through the valley between Laurel Knob and Cow Rock, across the Cashiers Valley near the base of Rock Mountain, and then down into Whiteside Cove. And the way the differential type of erosion, the speed up of erosion that you would get from fracturing across the top of that ridge offers a very plausible explanation for why all of those locations are today lower than the stuff that's around them. Generalization number 2, our country rocks, the Ashe Metamorphic, have lots of internal weaknesses, and they can fracture unevenly and at high angles. Why would they have internal weaknesses? Remember how they were formed. Lots of layering, variety of stuff getting piled on top of it in the bottom of an ocean, eventually getting pressed down, becoming rocks. But all those layers are going to create opportunities for weakness. Then they come along and they get bulldozed up, tossed and tumbled, a lot of stress. Again, lots of opportunities for fracturing, or at least weak areas to form. And then they got buried, and they got metamorphosed, which tends to put more layers into the rock. So one of the, I think this is seen at Schoolhouse Falls with this highly fractured, fairly angular fracturing that you have in that overhang. And you can also see it in rock outcrops. This is the top of Chimney Top. And you'll notice it's got this really raggedy, jaggedy surface. Well, if you look at the stuff, you'll see that these bumps that are coming up out of it are basically the tops of rock layers that are pointed up at a higher angle than the surface of this rock. And the erosion has worked away at the weaker layers of that that stuff angles up. It's gotten broken off, rounded off, and what have you. But you have this very raggedy surface. On a larger scale, remember Ashe Metamorphic is at the top of Whiteside Mountain. And you have this very sharp right angle cliff at the top. And you also, if you look at this surface, which is all Ashe Metamorphic, it's a very busy surface. There's a lot of stuff that's going on there. There's been a lot of weaknesses where the rock has been pulled away or formed up in rough surfaces in various ways. Now, compare that to this guy. This is Pluton down here. It gets steep, and particularly as you get down below the tree level there, but it doesn't drop off precipitously. It rounds down into its surface. And this surface is a lot smoother. It's not nearly as busy as the Ashe Metamorphic surface. And that leads me to generalization number 3. Plutons have few internal weaknesses, and all this is relative, and relative to the AMS. And it typically have shallow fractures parallel to their surfaces. All right, well, why would it have few internal weaknesses? Remember how it was formed. It was from a big pool of molten rock. It did not have bunches of layers. It hardened out of a fairly homogeneous liquid. It also did not undergo that process of being scraped up off the ocean floor. It intruded after that process had been completed. Now, if you don't think that the Pluton, the Whiteside Pluton, doesn't have many fractures in it, talk to somebody that's drilled for water, trying to go down and had gone down 800, 900 feet and come up with nothing but a lifetime supply of pale colored rock flour. And that's not uncommon in people that are trying to drill wells in the areas where the bedrock is Pluton. It also tells you something about how deep that Pluton can go. But now, it doesn't mean it doesn't fracture. And the way it does fracture is kind of interesting, and it has a big effect, I think, on what we see. The shallow fractures parallel to their surfaces. This picture will help you understand that. Now this is the big road cut out on 64. And ignore this really rough stuff down at the bottom because that's where the dynamite blasted. What I'm interested in is what that blast has shown about the fracturing patterns up above it. And you've got these fairly thin layers all parallel to each other and basically parallel to the slope of the original rock before it was blasted. And they're fairly smooth on top. This is called exfoliation fracturing. And it's just the outer skin of the rock popping off in onion skin sort of fashion, staying parallel to the surface. Now what would cause that? Well, there are probably two factors that are at play. The most important by a wide margin is that this rock is expanding. Why would that be? Well, remember, it used to be buried 8 to 10 miles. Huge amount of weight has been taken off of it over time, and it's still adjusting to that. Rock doesn't have to expand much to require fracturing and this doesn't expand a lot, but it does expand enough to need fractures to relieve the pressure of that expansion. Now, if you don't have a lot of other internal fractures, you're most naturally going to fracture in the way that is most natural for an expanding solid to fracture. And that's in this onion skin, superficial, parallel to the surface type of fracturing pattern. All right, what does that mean looking at the surface? Well, for one thing, it means we get nice white blobs on some of our mountainsides. Some of the weathered stuff pops off, and it lays white underneath. By the way, I didn't show you this earlier. If you don't, that gray that we see on our big rock faces, that's weathering. That's not the Whiteside Pluton. This is a Whiteside Pluton rock that I picked up out of a stream bed. When I cracked it open, that's what I got. Wow. It's a dramatic difference. That happens when when the surface, the weathered surface, pops off. One thing that may pop it off frequently on some of these rock faces actually is differential heating, particularly southern-facing slopes. The outer few inches of that rock will get a lot hotter in the sun and also a lot colder in real cold weather. Therefore, it expands and contracts more than the rock below it that is more stable temperature. And that will create some of this shallow type of fracturing as well. All right, the most famous of these blobs on the side of our mountains around here would be the Cow on Cow Rock. Now, you might think that the Cow is not as svelte as she used to be. Actually, exfoliation continues, but at least her younger, sleeker self is memorialized in the Lonesome Valley logo. It also, you can see this, on rock surfaces. This is a Pluton surface at the top of Rock Mountain. Just notice how dramatically different it is than this Ashe Metamorphic surface that I spoke of earlier at the top of its neighbor, Chimney Top. You can find these type of almost pavement-like rock outcrops that result from this fairly smooth type of fracturing, the exfoliation process, all around Panthertown when you're walking around down there. You also see it in the waterfalls, this kind of rounded nature, the smooth flowing. It shows up even more at Granny Burrell there on the left, and also at Wilderness Falls. Of course, Wilderness Falls is dramatically taller and steeper than Granny Burrell, but it has the same sort of continuous flow, rounded and smooth character, and a very different character than what you saw at Schoolhouse Falls. At a grander scale, this exfoliation process creates and preserves our dome-like mountains. These actually are called exfoliation domes. That onion skin fracturing retains the shape as they weather away. And this is all ways in which it has certainly, I think, helped me appreciate and I hope understand, hopefully not misunderstand, the ways in which the bedrock and that grand geologic story that I spent time on earlier have translated into the landscapes that we have today. Now, I owe you one more thing before I stop and we take some questions. And that is, what is the age of the Toxaway gneiss? You'll remember, I told you it was a lot older than the Raven granite, which is 335 million years. It's also a lot older than the Whiteside Pluton, which is 466. The answer, 1.2 billion years. Now, does that number ring a bell? That's the same age as that continental bedrock that our parent rocks got pushed up onto. What I alleged would be the beginning of this story. Something had to be happening 1.2 billion years ago. Well, plate tectonics, of course, in the form of the formation of the supercontinent Rodinia, which was the supercontinent that formed up, one that formed up prior to Pangaea. And just as with Pangaea, it pushed up a huge mountain range. It created underground magma pools, one of which became the Toxaway gneiss. It also created our continental bedrock. That's the bedrock that our parent rocks were pushed up onto. Rodinia lasted a long time. If you include some fits and starts and geologists arguing about whether maybe there was an intervening supercontinent, it was about 500 million years before the land masses really came apart and the Iapetus Ocean opened up. And of course it was the Iapetus Ocean into which the sediments from that former supercontinent were transported by river, became our parent rocks, and later were pushed up and became the country rocks of the Eastern Blue Ridge. It's all part of just an epic cycle. It's a cycle that continues today. It has gone far into the early history of the Earth, what it was going on before 1.2 billion years ago. And it's a cycle that will continue into the distant future. I am personally just feel very fortunate to be able to see the special places that have been brought to us at this particular point in that epic cycle. So that is Cashiers area geological history for about 1.2 billion years in a little over an hour. Back on the lights. I would be happy to take some questions, and there's one question that I kind of hope will come up, but if it doesn't, I'm going to jump in and answer it anyway. Yes, sir.
Are there any basaltic dikes readily accessible around here?
The amphibolites, I do not know of any as dramatic as that, but there is one. You can see them on the trail, the road trail going up to Whiteside. The National Park Service, or I guess Forest Service, had worked on that road, and in the process they lowered the rock that was on the right, and it cleared off some fresh road cut. And there are some sections up there where you will see this very black rock cheek by jowl with the gray rock that you see higher up up there. But that type of huge outcrop, I don't know of others that I've found. You know, of course, around here everything gets so weathered. We love road cuts, particularly fresh ones. Yes.
Do you have any idea what the temperatures of these 500 million years ago?
Yes. Whether I remember them accurately is another question. Metamorphosis is going to typically be between 300 to 900 centigrade. If it gets higher than that, stuff starts melting up. That gives you some, what does that translate into? 700 to 1200 or so, 1300 Fahrenheit. Yes?
What type of rock was it that came off of Bridal Veil Falls some years ago?
Bridal Veil is Ashe Metamorphic. And just look at it. I mean, if you compare it to the Panthertown, you would think it's Ashe Metamorphic. Anybody want? Yes.
Yes, I've got wondering what causes those white streaks on the face of bald rock above Lake Fairfield?
Yeah, the vertical white streaks. I think that is water flow keeping the weathering removed, so that the underlying rock is showing through. You know, they're all in water channels, and the water there is probably flowing fast enough and not staying there later that it's removing the weathering and not contributing to more. Yes?
The Foxaway DC you said was so much older than Whiteside. Is that the actual, where the waterfall comes down off the side of the road there?
Yes, it is. That is Foxaway nice.
Older than Whiteside now?
Yes, it is. Yeah.
The sign on top of Whiteside that says that Stone Mountain is also a Pluton? Is that correct?
That sign is simply incorrect. It says you're standing on a Pluton, and that is correct, but it's ignoring about 400 or 500 feet of intervening rock. And that's not just my take on it. The U.S. Geological Survey research geologist that mapped it, he says that's plainly the Ashe Metamorphic, as did the guy who mapped it 50 years ago. So, and it also, if you look at it and sort of apply some of the analytics that I do here of how the different rock surfaces are going to appear of the two types of rock, you'll conclude it's Ashe Metamorphic also. Anybody wondering why we have something called the Highlands Cashiers Plateau? Okay. First, I mentioned earlier, it is not recognized in the scientific literature. Most of what geologists would call a plateau are situations where there has been a known uplift event. Colorado Plateau, Cumberland Plateau. That sort of thing gets the geologists, research geologists pretty interested. They like to track that stuff. Ours, I've never seen anything written about this. I'm working this out on my own, so I'll take it for what it's worth. I don't think there are no known faults around the area that would relate to an uplift event. Also, if the plateau, what we call the plateau, and I call it, even if the professional geologists don't want to, if it had been an uplift event, our mountains would also have been a lot higher than the surrounding mountains. They're not. Mountains, not too far away in the region are higher than our mountains. It's our valleys that are the difference. Our valleys are 3,000 to 3,800 or so. You drop down off the mountain, and the valleys are 2,000 to 2,500. That's where the big difference is. So what might have accounted for that? Well, since nobody had ever prepared defined the Highlands Cashiers Plateau, I had to define it for myself to try to do any inquiry into this, and that's where this map came from. This black outline is roughly the area within which all the valleys are at 3,000 feet or higher. You can argue about whether that's a good definition of the plateau, but that's the one I used there. I got the locations of the various plutons off of about a half a dozen different geological maps of various scales, and just colored it in myself. Now, what does this tell me? I did this because you'd think the plutons must have something to do with this. And I think it may not be a complete answer, but I think it is something that has contributed significantly. You've got the Whiteside here, basically the floor of the main valley. Then you have this higher stuff over here that's really not so much an issue. You've got some higher stuff in here. And then you have the Toxaway and the Raven sort of holding up these edges. Well, how might that have worked? Well, here in the center of the valley. Now, I told you earlier that probably because of that folding and the fracturing along the ridge, there was a lot of erosion, came down, formed a valley. Some of that erosion would have been going through the Whiteside Pluton, there isn't any question about that. And that's a case of generalization number 1 making an exception to generalization number 3, where I said that the Whiteside Pluton didn't have a lot of fractures. But once that erosion got down into the Whiteside Pluton, my hypothesis is that while it was fractured, it continued to erode. It does not have as much internal fracturing. It doesn't have as much openings to erosion as the stuff out in our valleys, off the mountain, where you get a lot of the Ashe Metamorphic or similar rocks. And the erosion simply slowed down. It just hasn't eroded up here as fast as it has down in those rocks in the valleys. Now, the role that I think these guys on the edges have played, same thing there, water going over those relatively smooth surfaces. It hadn't eroded away real quickly. It has helped kind of keep the elevations over here on these edges higher. That means lower stream gradients, slower stream flow, and less erosion. Now, where you can really see that is up here at the Raven Pluton. I told you it went right over the spillway at Lake Glenville. What happens after you go past the spillway at Lake Glenville? The world drops off. Gets down to 2,000 feet real quick. This baby also goes right along the top of Kulisaja Falls. What happens after you pass Kulisaja Falls on Highway 64? The world drops off. So, this is not, there are some issues with this, but I would love to see geology department somewhere decide they want to do some research to prove or disprove that hypothesis, but it helps me feel like I understand what's been going on. Anything else? You've been a great audience, very patient. I'd be happy for you, if you have individual questions for the conversation, I'll be here for a little while. Happy for you to come up and look at these samples, play with them. I've got some sort of lay-oriented resources that I have found that you might be interested in knowing about. Happy for you to look at those. And there are a couple of geological maps that we put up over there. The one on the right is fairly easy to figure out what that is. It's the Appalachians. It's a U.S. GS map, very large scale. The one on the left is the graduate department of University of Tennessee at Knoxville, which has a very well regarded master's and doctorate program down there. The mapping that they did that covers Panthertown. So you can find some Panthertown locations on there. If you're having trouble, come get me. I'll see if I can help you find them. The one thing you will discover if you start reading the what rocks go with what colors, and this underscores the complexity of that Ashe Metamorphic. You'll see a nice crisp line, and this is one version of Ashe Metamorphic, and here's another version of Ashe Metamorphic. You read the fine print, and it says, oh, they're all intermingled, and there's just a little more of this one version where it's gray, and a little more the other version where it's purple. It's very complex stuff. Anyway, thank you very much.
Thank you very much, Bill. We appreciate you being here. Thank you for giving the presentation. Folks, we're not getting out of here just right now. You're all welcome to go get some food. Come on up here and ask any questions you have. But real quick, before we do that, we want to give away a couple more things. We got some door prizes, so get your door prize ticket out. And we're also going to be giving away this big Yeti cooler. So if you've had a chance to meet my daughter, who has politely come up to you and asked if you'd like a raffle ticket, she will be drawing the ticket. We got them stirred up real good here for you. All right, we're going to give away a map. This is one of Bert Cornegie's Guide's Guide to Panthertown Valley. It is the best reference for all your adventures in Panthertown. If you haven't already gotten yourself a copy, we recommend you get yourself one, and Bert's here to autograph it.
Yeah, Bert is here tonight and might be willing to autograph a map.
If you like, yes. So our first prize will go to 615-315. 315, are you still here? Going once? 615-360. All right, we have a winner for a Bert. She's going to bring you the map. Our next prize is a map from the U.S. Forest Service, which has the official trail system, 30 miles of trails in Panthertown that our organization maintains. 386. 386. 615, if you didn't know. All right, next one. See, you still have a chance. 328. 328. Did we get one? All right, we got a winner. You can bring it to them. And our last prize for our door prize will be a t-shirt of your choice. You get a size and color of your choice. And that will be 391.
Great Baldwin.
Well, thank you for buying a t-shirt. Would you like another one to give as a gift? Would you like one?
Yeah.
All right, he's going to come up and get one. Thank you everyone for participating and having your door prize. Now, if you have a raffle ticket, get it out because we're about to raffle off this beautiful Yeti cooler here that was gratefully donated by Zoller Hardware right here in... She wants to buy it?
No, she's selling one more thing.
No problem. We're going to do about 5 minutes, so I'm leading up to that. We do have some raffle tickets available. We printed 400 raffle tickets, which the odds of winning, if you buy one raffle ticket, is 1 in 400. However, if you buy 5 raffle tickets for $20, your odds of winning are about 1 in 80, which is less than the people in this room. So you have a better chance than all the people that are here. We do have some food still in the hallway there, and there are still opportunity to ask questions if you'd like. Like I said, we're going to give you about 5 minutes if you want to get a raffle ticket. In the meantime, thank you so much for being here, and in about 5 minutes I'll come back and announce the winner.
Hopefully,